So I have in my notes that I'm supposed to go through the solutions to these. I can't remember which ones we did in class, so let's just go through all of these to figure out how to do this. So, and after we're done, we'll hopefully have a good idea of how to find eigenvalues and eigenvectors. The way that I do this is I'll start off by writing the matrix, and I'll put the lambda on the diagonal. And then we're going to do the determinant of this new matrix, so the determinant of this. So 1 minus lambda, 4 minus lambda, minus 18. So let's see, this is going to be lambda squared minus 5 lambda plus 4 minus 18. It's going to be minus 14. And this we're going to set equal to 0. This does look familiar, so we must have done this one in class. But here we go, plus 2. So lambda is equal to 7, and lambda is negative 2 are the two eigenvalues. And then to find eigenvectors, we're just going to plug those in one at a time. So first one is lambda is equal to 7. And then we will do the lambda is equal to negative 2 over here. Each case, we're going to just do basically plug that lambda in up here in the matrix, and then essentially find a solution to this. So let's see, 1 minus 7, through 6, then 3, then 4 minus 7. I'll do it a little bit quicker over here. 1 minus negative 2 is 3. That's not quite right. Oh, negative 2. Sorry. 6, that's better. And 4 minus negative 2 is 6. So that looks better. So we'll just do this. So what we're going to be left with on the left, I believe I have negative 6x. We'll just call this vxy. Plus 6y is equal to 0. Then 3 minus 3y equals 0. Those are the two equations. Essentially, 3x. Essentially, x equals y here. This, you're going to have 3x plus 6y equals 0 for both equations. And so in this case, x is equal to negative 2y when you solve this. So my eigenvector, we'll use this vector 1. It's just going to be 1, 1. It can be anything that has the same top and bottom, the x and y. As long as x and y are the same in this one, as long as x is negative 2 times y, you're okay. So that's that one. I don't know if we did this one. Let's try. So 1 minus lambda, 1. And then this is going to be 1, and then 2 minus lambda. So give me a minute. Determinant. So this is going to be lambda squared minus 3 lambda plus 2 minus 1, which is, I remember this one. This one was yucky. So we've got negative b plus or minus the square root of b squared minus 4ac over 2a. And so let's go ahead and do it, I guess. So 3 plus radical 5 over 2, and 3 minus radical 5 over 2. So we're doing this for this one. Let's see. Let's see, this is 2 minus 3 plus radical 5 over 2. And this is going to be something similar. In fact, it's so similar that I'm just going to maybe I'll do the work and then copy it, because it's almost going to be the same. Okay, 1 minus, let's see, this is going to be negative 1 minus radical 5 over 2 times x plus y equals 0. X, and then plus, it's going to be negative, or 1 minus radical 5 over 2. Interesting. It's the golden ratio, both of those actually. That's a y there. And these will give you exactly the same expression, especially given its golden ratio. I can tell that that's what's going to happen, but you can do the math if you don't believe me. But so here's what I'm just going to do is I'm going to do this. If you solve for x in both cases, you'll get x is equal to the negative of 1 minus radical 5 over 2 times y. So let's let y equal 1, I guess. And then negative 1 minus negative radical 5 over 2. And that's going to be my vector. Got to do this. Oh, that's right. I can just copy and paste. Because this is so similar, probably, well, we'll see. Let's duplicate, and we'll just go correct the things that we need to correct. So the main difference here is that that's going to be 3 minus. Oops. There we go. And that's going to put a plus here. Whoops. Be plus here. And then this will be the negative of 1 plus, which is still the golden ratio. The golden ratio is interesting. Well, okay, since I've mentioned it, this is the golden ratio. And if you do the reciprocal of this, you get 1 minus, radical 5 minus 1 over 2. So, anyway, let's move on. So a whole bunch of problems here. I don't feel like doing all of them. Hopefully letter B, or let's do C, since we haven't had a C yet. Let's do C, see if this works out. This isn't the same, is it? No. Okay, so basically I'm just doing the determinant of this matrix. Just feels familiar. So this is going to be lambda squared minus 4 lambda plus 3 plus 2 is plus 5. Okay, this works out nicer. Oh, it doesn't work out nicer. Did I do my math correct? 3 times 1 is 3, plus 2 is 5. And then, yeah, well, I was wrong. That's not going to be a nice one. So 4 plus or minus square root of 16 minus 20. Ah, this is nice in its own way. Okay, so this will be lambda is equal to 2 plus or minus I. So I'm using, so the square root of negative 4 is the square root of 4 times I. So that's 2I. And then when you divide by 2, you get just positive I. So, yeah, you get complex eigenvalues, which ends up resulting in no real, the eigenvectors aren't real, so there aren't any straight line. What this indicates is that there's going to be, it's a rotation. This is a rotation in terms of the, like what this does to a picture. So here, you got to pretend that's a picture of someone. So that means this rotates and probably expands a little bit because of the 2. So I think I'm just going to leave that one like that. Okay, let's do 1 3x3. I feel like we did one of these in class. Let's do this one just for a change. Wait, did we do that one? Which one did we do? Let's do this one. So we're doing the determinant of 1 minus lambda, 0, negative 1. 1 minus lambda, 0, 2, 0. Okay, so to do this determinant, we're gonna, I'm gonna do the whole, copy the two diagonals, or not two diagonals, two columns. Oh, I didn't mean for that to happen. That's weird. Let's delete that. Delete. Okay, I just have to write it. So 1 minus lambda 2, 2, 0, 1 minus lambda 0. And then I'll do the diagonals. So this is the trick that you can do with 3 by 3 matrices. Down diagonals. Looks like the only one that's going to be non-zero is this one. So that down diagonal, I can't factor out negative 2. What am I doing? Let me just leave it the way it is. I thought I was being cool, and I was being dumb. Okay, so there's the down diagonals. Now we do the up diagonals. Looks like only one of them is going to survive. And so you'll be left with minus negative 2 times 1 minus lambda. So let's see. I've got to do some foliage here. Give me a sec. Okay. Trinomial times a binomial. Negative 2. Let's see, that's going to be positive 4. So 3 lambda. Then 2, 2, 0. So there's no lambda squared. And then lambda cubed. Okay, well this is nice because I get lambda minus, I should write equal signs, lambda cubed, which is easy to factor. It's lambda times 1 minus lambda times 1 plus lambda. So I have lambda equals 0, lambda equals 1, and lambda equals negative 1. So let's start with lambda equals 0. Sure, why not? So here we go. So I'm just going to copy. I know that I can't just copy and paste apparently, but we can do this. 1 minus 0, 0, negative 1, 2, 1 minus 0, 0, 2, 0, negative 2 minus 0. So I want to find x, y, and z for that. That is so big, it's bleeding over into my next spot. So let's do this. I can copy this. There. I'll just do that again. There we go. I've got all of them. Let's put some lines in. Okay. So this one becomes 1, 0, negative 1, 2, 1, 0, 2, 0, negative 2. So z. There must be a free variable here. So that's the whole point. So, oops. Yeah, let's just get rid of this because we're not going to do this one. Okay. So let's just set this up. X minus z equals 0, 2y plus, no, 2x plus y equals 0, and 2x minus 2z equals 0. That's what those three equations are. Presumably this will, I suppose I should have just done row reduction. That would have been easier. Yeah, let's do that. Let's work with the matrix. Let's work with the tools we got. Okay, so we're going to subtract 2 times row 1 from row 2 and from row 3. So let's see, this stays the same. This becomes zeros. This stays the same. We're subtracting 2 times row 1 from row 2. So 2 times -1 subtracting becomes positive. Subtract 2 times, whoops, sorry about that. 2 times, so it's going to be -2. So that becomes 0. Ah, there's my zeros. Excellent. Okay, so we've got x minus z equals 0 and y minus plus 2z equals 0. So z is the free variable. So you can pick any number you like for z. Let's pick 1. X is going to be the same, and y is going to be negative double the z. So there's my v1. Hopefully these will go quicker. In this case, we're going to get rid of the 0 and put a 1 in there. And so this matrix becomes 0, 0, -1, 2, 0, 0, 2, 0, -3. Column of zeros. Okay, so let's see. So y is the free variable. But we got to figure out what x and z are. So let's see. I'm going to subtract. How about subtract row 2 from row 3? So I have -1, 0, 0, 2, 0, 0, 0, 0, -3. And then subtract or add 3 of row 1 to row 3. So the long and the short of it is that negative z has to equal 0 from that row. This row says that x has to equal 0, well, 2x. So z and x have to equal 0, so v2, but y can be whatever we want it to be. So let's pick 1 for y and zeros for x and z. Last one. Let's see, we're going to add 1 because that's subtracting -1. So my matrix looks like this. Okay, well, we have the same row, top and bottom. So let's just leave it the way it is and call it a day in terms of, the top and bottom row say that z has to equal 2x. If you take either of these, that's what you get for your equation. And this one tells you that y has to equal -x. So x will be our free variable. Pick whatever you want for x. And then y has to be the negative of that, and z has to be 2 times that. So that's my eigenvector. Hopefully this helps, and we'll see you on Thursday this week.